Okay, this next problem deals with nuclear accelerator, kind of like perhaps the Large Hadron Collider. So, the way we're going to solve this problem is we're going to, first of all, take an electron. And an electron is accelerated in a particle accelerator. And the question is, how fast does this electron have to go in order for it to be 100 times more massive, as seen by an observer, not in the same reference frame? So, basically the problem here becomes that if we have the rest mass and the relativistic mass, the relativistic mass is going to be 100 times the rest mass. Okay? Question, what velocity, how fast does it have to go in order for that to be true? Well, the equation is m equals m naught divided by the square root of 1 minus v squared divided by c squared. Now, if we have this relation where we say m equals 100 m naught, then what we'll do is we'll just replace it. So we'll do substitution. We'll take this variable here and replace it with 100 m naught. And that's going to equal m naught divided by the square root of 1 minus v squared over c squared. And now, of course, you see we can cancel out the m naughts. And we're still looking for v. So at this point, what we would do is let's reciprocate 1 over 100. And let's reciprocate over here, 1 minus v squared over c squared. And now let's square both sides. So we'll get 1 over 100 squared is equal to 1 minus v squared over c squared. And now we want to isolate v. So let's take this term to the left hand side of the equal sign, and let's take this term to the right hand side. So we get v squared over c squared is equal to 1 minus 1 over 100 squared. And continuing up here, let's just draw a line. And continuing up here, we will have v squared is equal to c squared times 1 minus 1 over 100 squared. And if we now take the square root of both sides, we get this. Now, that turns out to be approximately, taking c equals, of course, c is equal to 3 times 10 to the power of 8 meters per second. Therefore, v is equal to 2.99985 times 10 to the power of 8 meters per second. Okay, so that's how fast this electron has to be going in order to be 100 times more massive. Now, the next part of the question says, if the distance through which the electron accelerates or travels is 30 kilometers, how long does the electron see the distance as? So the question more specifically is, to achieve this speed, electrons may be accelerated through a tube that is 3 kilometers long. How long does this tube seem to be to the electron moving at its final speed? So this 3 kilometers, now 3 kilometers, this is also part B. So what are we measuring here? What is the 3 kilometers? Is that the distance as seen by who? Who does the measuring here? So this 3 kilometers is measured by a person not in the electron's frame of reference. Okay? So that means it's by a person who is not moving with respect to the 3 kilometers. So that means it's L naught. Now, how long is this as seen by the electron? Well, that's L. And that's equal to, hold on a sec, I'm going to start this later. We'll come back to this problem.